This is a hydrothermic engine progress update. This is the new test unit that I built, but its construction is pretty much stopped in its tracks. The reason for that is some data I came across during research. But I'm going to go ahead and give you a rundown of the test device because I am going to be able to get some data out of it and it will be of some use. Basically what we're looking at here is a double valve unit. When it's in the up position, this side is open, the steam and the coolant water is off. When it's down, the opposite takes place. The steam shut off and the coolant water is turned on. And if you haven't seen the previous video of what's inside this thing, it's basically a heat exchange like this with copper tubing of that exact diameter ran through with an end cap put on it. And the heating oil is inside the cavities between the tubes. The tubes have either steam going through them or coolant water. The problem with this setup is that I've decided I am not going to be using steam as a heat source. It turns out that thermal heating transfer fluids are far more efficient. So I'm going to veer away from this concept and this particular configuration altogether, because I think that it would be better to have a unit like this. Or better yet, let's look at what we've got. If I instead put the heating oil inside of a tube like this, inside of this coil of copper pipe, and then connected this unit to a manifold and had, like, say 25 of these things or something, maybe not that much. We'll start off, I want to try to build like a 4-cylinder unit. So if we had 4 of these hooked up to a manifold system that would fluctuate or cycle between hot and cold, have one pump pumping hot fluid through it and one pumping cold fluid depending on the valves. We could have solenoid valves. Hot could go in here, cold can go in here, with a solenoid valve here and here, and of course the proper porting on this end of the unit. This is not how the pipe would go through there. It's probably going to be smaller and a bigger pipe. The coil won't be as tight and all that good stuff. But I think I'm going to veer away from the container because that thing only can hold, I think it was 2,500 psi's. And with this tubing, I can get a lot more pressure. I don't know what the bulk modulus of the oil I'm going to use is yet, so over 2,500 psi's may not even be possible. But before I bore you to death, basically what we have here on the steam generator that I am going to use on the test is a 3,000 psi oxygen tank with a propane torch hooked up under there. And it's got a little tether here for my tank, and I've got a water pump hooked up to a router. And what I'm going to do is get everything running and hooked up, and I'm just going to sit here and cycle between hot and cold, and I'm going to see how long it takes for it to cool off, how long it takes for it to get hot. And then I'm going to do some pressure testing and see what type of pressures we get in those fluctuations. Hopefully we'll see this thing hitting 3,000 psi, but I'm thinking the bulk modulus of this oil inhibits that and would render us in the area of about 2,500 psi or less. I thought I just blew the bottom of this thing out. Apparently not. Now we're approaching 500 psi right there. 600 psi. Almost 700 psi. I really don't want to be standing next to a pressurized vessel of hot oil today, but the things I do. See its pressure dropping rapidly. I got some oil leaking out the bottom of this thing here. I thought I blew the chamber. Maybe I did. It's just a really small leak. And that's why the pressure is dropping so drastically. So that's kind of cool. I am getting some footage of pressure up. But the heat exchange ruptured at 500 psi. I did not have this on footage earlier, and I was really angry with myself. But I'm happy to see that it's just a hairline crack. going to go ahead and pressure this up one more time. So this is another reason I don't like this design. I had to use silver solder. Trying to get a good focus here. Just not having much luck. Okay. Leaking oil out. Pressure not pretty good. Coming up to 600 psi again. Still got that drip. So I've blown the manifold. This thing's plagued with problems. The design was flawed from the get-go. I'll get into that later. Earlier I got over 15 cc's of volume increase from a short burst of energy like you just seen. And it created a gas pocket inside the top of this chamber, which rendered the device inoperable from that point. So any fluid that's used in this system is going to have to be purged of any gases that are dissolved in it. Yep, that's a hairline crack because it is not holding that pressure, and I doubt that it's cooling down that quick. So we're hitting 600 psi's. I'm afraid to go any higher. The fact that I busted this thing open at 500 psi's is good news and bad news. I mean, I guess if it don't break, it ain't going to work, right? So, let's do that one more time here. All right, I'm going to get crazy here. Can't really see this thing very good. Ready to start on fire at this point. I'm going to get a temperature reading. 90 Celsius there. 500 psi. 90 Celsius. Serious pressure there, almost approaching 1,000 psi. I'm showing 84 Celsius. I'm not showing much increase in heat at all. I'll go over to the data there. Yeah, I definitely have a hairline crack. Pressure's already dropped. There's no way that's due to cool off. So, I don't know if you hear that. Making some crazy noises. I'm going to crack the valve. Yeah, that's not a very good sound. Probably boiling oil in there at this point. She's hot. And busted. So, based on that failure, the best design is going to consist of something like this. There's going to be a coil with the oil inside the coil that is slid inside a tube, not with this type of end. The end will have this on both sides. The coils will be protruding through this cap somewhere, and there will be hot and cold connected to each end of this. There will be a solenoid valve for the hot, solenoid valve for the cold, and it will cycle between hot and cold, heating and cooling oil in a bunch of these units with check valves, creating an extremely high pressure hydraulic pump that will make a heat engine with efficiencies that should be above the 40% barrier that most machines are currently seeming to be around. Diesel engines are so far the most efficient engines that I've seen, except for power plants, which are big enough to be more efficient. So one of the reasons I'm not using steam heat in the plan anymore is because something I found out. Oil heating systems are 30% more efficient. This is some of the data I got from some research I did. And in order to get a 200 degrees Celsius steam system operable without a superheater, I would need to run it at 16 bar of pressure. That's about 232 psi's. So an ideal system would have a tube like this with a coil similar to this here inside of it, and a bunch of these connected in tandem to a manifold with, you know, proper check valve arrangements and all that. And I don't have any of the we're probably not going to be able to see much of this. Actually, that's pretty freaking cool in here. Anyway, I don't have the drawings on this page, and I can't find it with my camera on, but I'll get back to that. So I'm straying away from these heat exchange type designs. They just can't hold the pressure. Somewhere along one of these solder joints, it busted. It's still leaking oil out, it looks like. Got a nice little puddle going there of oil. So I blew that up, which is good. I mean, I don't like the design in retrospect. I'm going to go back to this, the coil system. I think this is going to be way better and way easier to manage. And as soon as I get some good check valves, this thing ought to be up and running.